Now, once we have the correlation coefficient, we actually need to be, again, a little bit more rigorous in our definition of if it is strong enough, right? So we have the scatter plot and we look at it personally and we say, okay, that looks like there's a pattern. Then we find our R value, that correlation coefficient. And again, like in the last example, our R was pretty high. It was over 0.8. So again, that seems pretty strong to me. But we need something a little bit more precise and something that everybody can agree on, right? So that we're not all just saying, well, that seems strong enough. So we do have a way to make this a little bit more rigorous. Once you've calculated R, the sample correlation coefficient, you will want to determine if there is enough evidence to decide that the population correlation coefficient rho is significant. So in statistics, we take samples to make conclusions about the population. So we want to know, is our R strong enough so that we can apply this idea to the whole population, right? Our sample size was only 10. Maybe that's not enough. Even though our R is high, maybe because the sample size is so low, it's not strong enough to make this conclusion applicable to the whole population. So there's two ways we can do that. One is using the table in the back of our book, and another is with hypothesis testing. So we're going to use the table first. Now, just one thing as a side note, R is your sample correlation coefficient, and then rho is the population correlation coefficient. Okay, so it looks like a P. It's not a P though. It's actually a Greek letter R, lowercase. It's not spelled this way, but it's pronounced row, like as if you row a boat. So when you see this symbol that looks like a P, it actually is the Greek letter R, because remember, we like to use Greek letters for population. So it is the Greek letter R. So it means the same thing, just for the population. Now, to determine if R is significant, we use table 11 in our text in Appendix B. You also have to choose a significance level alpha, similar to how we've done it before with hypothesis testing and things like that. Now, your alpha represents your error. So your alpha basically equals your error. So in correlation studies, the alpha gives a percent of times that you decide a correlation is significant, but really it is not. So for instance, if alpha is 0.05, then what that means is 5% of the time that you decide that the correlation is significant, it's actually wrong and it's not. So that gives you a chance of error when making your conclusion. So how do you use table 11? First, obviously, determine the sample size. So how many pairs of data do you have? Make sure you specify your alpha. And then this is like the critical value method for hypothesis testing. You're going to find your critical value in table 11. And then what happens is if your R, the absolute value of it, is greater than the critical value, then the correlation is significant. So that's how you decide. You want to see if your R is bigger than the critical value in the table. Okay, so let's try our example here. So in the example that we've been working with in these videos, we have found our correlation coefficient was about 0.874, which we said seemed pretty strong, but we only had 10 data points, so our N is 10 here. So let's see if this is actually strong enough. So what I'm going to do now is I'm going to show you guys the table 11 in the back of the book. So just give me 1 second. So here is table 11 right here. And you can see that it's set up where you have your alpha, your two alphas. These are the two most common ones we use. And then you have your sample size. So for us at N is 10, and we're choosing an alpha of 0.05 here, the critical value is 0.632. Okay, so 0.632. Just write that down. All right, so from table 11, our critical value for alpha equals 0.05 was 0.632. So now we compare that. So compare RR with the 0.632. And the absolute value of 0.874 is just 0.874. And this is definitely bigger, right? So since R is bigger than 0.632, the correlation is significant. So this is the cutoff for that sample size, an alpha of 0.05 to be significant, right? So if anything is, if your R is bigger than that, then it's going to be significant. So it's not just us guessing, okay, is 0.8 significant? Does that seem big enough? We actually have a system in place now where everybody can agree on that, well, for a sample size of 10, an alpha of 0.05, as long as your R is bigger than 0.632, we all agree that yes, that's significant. So now I have really three things that have told me that we do have correlation here. I saw my scatter plot. I calculated my R value, which seemed to be pretty high to begin with. And then now I looked at my table, I found that critical value. And now I can really be more confident that there does seem to be a correlation. Do keep in mind that there's always a chance of error. So because our alpha is 0.05 here, we do have a 5% chance of error that we are wrong, right? That there really isn't correlation, even though there does seem to be. So what would have happened there is we just got a sample that wasn't a good representation of the population. But based on everything we're seeing so far, it does seem like we have some good correlation here. All right. Now, using the table, so kind of using a critical value approach works, but you can also use hypothesis testing here too. So I'm going to show you how that works as well. So you can use a hypothesis test to determine whether the sample correlation coefficient provides enough evidence to conclude the population correlation coefficient would be significant. And a hypothesis test for row could be one or two-tailed. So if it's one-tailed, left or right-tailed, it would look like this. So this is how you would set it up. If it's two-tailed, it's set up like this. So it's a little bit different than our usual setup that we're used to. So we're using 0 here because 0 means there's no linear correlation. So that's why that 0 is being kind of used as that centerpiece. Okay, and we're again trying to decide also what kind of correlation there is. So basically here you have your row is less than 0 because we're kind of trying to claim that there is a negative correlation. Here for the alternative hypothesis, your row is greater than 0 because we're trying to claim there's a positive correlation. And then here, if it's not equal to 0, we're just saying that there is a significant correlation, but we haven't classified if it's left-tailed or right-tailed in any way, so positive or negative. In our text, we're only going to focus on the two-tailed test. So again, we're just going to kind of narrow it down and keep it to more of an introduction here. And here is our test statistic. So new formula. So we do use the t distribution to find this. So a t-test can be used to calculate whether the correlation between two variables is significant. So the test statistic is R and the standardized test statistic. So here's the formula you're going to use here. It does follow a t-distribution. Be careful with degrees of freedom equal n-2 here instead, where n is the number of pairs of data. So the degrees of freedom is different because 1 degree of freedom is lost for each variable. So here, because you have 2 variables, you have to subtract 2 to get the degrees of freedom. So to hypothesis test, you're going to start the same way. We're going to identify the null and alternative hypotheses. We're going to make sure we specify the level of significance. We're going to find the degrees of freedom. And then we can go back here and using table 5. We're going to just kind of stick with the critical value method here and just do one method in this section instead of the p-value and the critical value method. And then we'll find our test statistic and decide if it falls in the rejection region or not. And again, like we said before, we are going to assume for right now that these requirements are met. So don't worry too much about the requirements in chapter 9. We're really just kind of looking for an introduction to this topic here. So let's do our example. All right. So in example 4, so again, I'm sticking with the same example. We found the correlation coefficient was about 0.874 with 10 data points. Is it significant? We're going to use the same alpha, but this time we're going to use the hypothesis testing technique. So again, I'm going to skip the requirement check here because our text has said that we can assume it's fine. We're not going to, again, worry too much about that section here. And we're going to start with our setting up our hypotheses. So your null hypothesis is going to be that rho equals 0, which means that there's no correlation. And your alternative hypothesis will be that it is not equal to 0, which means that there is significant correlation. And again, for our text, we're just going to stick with a two-tailed test here. So we're just determining if there is significant correlation or not. All right, after we do that, we're going to identify the level of significance. So our alpha, we're told, is 0.05 here. And then our degrees of freedom is n-2. We have 10 data points, so our degrees of freedom will be 8 in this case. Okay, so now we have our setup. We have our null hypothesis, we have our alpha, we have our degrees of freedom. And if we're just following along with the steps on the page before, the next couple steps have to do with finding our critical values and then also with finding our test statistics. So we're going to work on this next. And for me, you guys know I always like to draw a picture here. So I'm going to kind of combine steps 4 and 5 together. So we're doing a two-tailed test here. And again, we're going to focus on the critical value technique here. I don't want to do too many different techniques for this section. And our alpha is 0.05. So because we have two tails, we're going to cut this alpha in half. So we're going to divide this by half. And so you're going to end up with 0.025 or 2.5% in each tail. Now, don't forget we're doing a t-distribution here. So if you go back to the setup on the page before, this is a t-distribution, not a z. So what you can do to find those critical values, you can use your table in the back of the book. You can use your technology. Either way is fine. I'm going to use the table just because it tends to be the fastest way with t-values for the critical value method. So yeah, let me just go ahead and find it. All right, sorry guys, I'm just getting the table out here. So here we go. So this is table 5. And you just want to be a little careful. So remember our degrees of freedom this time are going to be 8. It was n-2. And here we're talking about an alpha of 0.05, and that's in two tails. So we're looking at the 0.05 in two tails, or if you look at your picture, that means you have 0.025 in only one of the tails, right? So we're in this middle column here. And we're just going to go down till we get 8. And we see our value is 2.306. So don't forget, I'm lining up the row, which is the degrees of freedom, but also my alpha. So my alpha for the two tails combined was 0.05. So that's what I'm looking at here. In only one tail, my alpha is 0.025. So I'm in this middle column here, and I'm getting that value of 2.306. Now, remember here, there's always a positive and a negative value as well. So if I kind of go down to the test piece, so the value given is the positive one, but we can also make it -2. All right, so our two critical t values, this one is going to be -2.306, and this one is positive 2.306. And again, I just use the table in the back of the book here, which is pretty easy. We also need to find our test statistic. So using that formula on the page before, this is the formula we're using. Now remember our R we said was 0.874. So we're just going to plug that R in here. And then our N value was 10. And using your calculator, you can try this part at home, you should get about 0.5087. So 0.5087 is going to lie way, way, way over here, right? So here our critical value is 2.3. So it's probably somewhere way over here, even further. So it is definitely in the critical or rejection region. All right, so remember those shaded regions are your rejection regions for the null hypothesis. So in this case, we are going to reject the null hypothesis. Now, think about what that means here. Our null hypothesis was that there was no correlation, and we're rejecting this. So that must mean that there is significant correlation here. So there is significant correlation based on a significance level, oh, sorry, I should say of alpha equals 0.05. Okay, so remember there is based on a significance level, right? So there is always a chance that we're wrong, but given all the data that we have here, it is showing that there does seem to be significant correlation in this case, or linear correlation, I should say. So for hypothesis testing, just remember that we're focusing on this setup here. So you don't really have to choose so much what values you're plugging in. We're using that 0 as our null hypothesis. And then the other steps are pretty similar. So you are using a t distribution here, just like we've done before, and they're using the critical value method in this case. So you have a new test statistic, right? But a lot of the same procedures are here that we've seen before. All right, now just a little side note, in case you are using your calculator, then if you remember back to the previous video, or I should say the previous video, but previous videos, we were able to find the R using technology. So even though we're using our, our formula here to plug that R in, I would still recommend using technology to find that R and then come back here if you're doing hypothesis testing and then do the rest of the procedure, even if you have to do some of it by hand or with the table. So again, still try to find that R using technology. That's usually the easiest way to go ahead and do that. Now, one last thing I want to make clear here, and this is actually really important, is that correlation and causation are not the same thing. So the fact that two variables are strongly correlated, let's just say does not mean that there is necessarily a cause and effect relationship. So two variables being correlated does not mean that one causes the other. And this is a big thing that many students and just people in general mix up. They kind of assume that if there is a relationship between two variables, then one must cause the other, and that is not always true. So more in-depth study is usually needed to determine whether there is a causal relationship between variables. So what we're doing here is we're showing that there is a correlation. We are absolutely not proving that there is causation. That requires more study. When there is significant correlation between two variables, a researcher should consider the following possibilities. So one, there could be a direct cause and effect relationship between the variables, and that is, you could ask the question, does X actually cause Y? So you have set it up where X is independent and Y is dependent. So is that actually the case? And again, what we're doing here is we're not proving that. This would actually have to lead to more research, more experimentation, etc. There is a second question you can ask about cause and effect. And that could be that, do you have the variables backwards? Is there a reverse cause and effect relationship? So maybe when you graph, you mix them up. Maybe Y causes X, right? So that's something else that you could think about. The third thing is, and this is actually a lot more common than maybe you think, is that it could also be possible that the relationship between the variables is caused by a third variable or a combination of several other variables that are not necessarily being studied. And a great example of this, although it is a sad example, would be something like ice cream sales and drowning deaths. So both of these increase during the summertime, right? People buy more ice cream when it's hot out, more people are swimming when it's hot out. So ice cream sales and drownings, although there is a correlation, they likely both increase together and decrease together. One does not cause the other, right? So the hidden variable there is the heat or summer or some other temperature factor. Another example that your book gives is, let's say someone goes to a restaurant and they have a allergic reaction to the meal that they receive, right? So they may be assuming that maybe there was shrimp in the dish. Maybe they're allergic to the shrimp in the dish, right? They haven't had shrimp before, so they had an allergic reaction. It must be the shrimp. But perhaps it wasn't the shrimp, maybe it was the seasoning, right? So you may think that you have an allergic reaction to shrimp here. It's a food that you haven't eaten before. Shrimp tends to have a lot of allergies associated with it. But in fact, there actually is another variable going on here, and it actually wasn't the food. Perhaps it was the seasoning. And again, these are things that we can't prove without further research. The last thing is that sometimes it could just be coincidence, right? So is it possible that the relationship you're observing between two variables just happens to be coincidence, okay? And that could happen too, right? So you do want to be careful. Just because we prove that two things are correlated, it does not mean that one causes the other. It can, but if it does, it requires further research. And this testing that we've done here is not enough. So you would have to go in and do a lot more research to actually show that one variable does in fact cause the other.